Good afternoon, everybody. Thank you. My name's Simon Kelly. I'm the current Dean of the Science, Technology, Engineering and Mathematics faculty, and I'm here just to do a very quick introduction. So, welcome to the Open University. We hope that you enjoy this series of talks. You're going to hear from four really interesting people. Thank you. Eleni Wood, who's a geologist, is going to talk to you about Himalayas. Uwe Grimm is a mathematician. He's going to talk to you, I'm guessing, about quasi crystals. Yeah. Karen Olsen-Francis is a microbiologist, ecologist. It's a really interesting take on what you can do with bacteria and what they mean. And Trevor Collins, who is an educational technologist, set there. Trevor does all sorts of things, and that's just one of them. I'm really going to stop waffling as soon as I can because I think it's more important and more interesting for you to be listening to the first speaker. So I'm going to ask Eleni. Eleni is a current PhD student, so of the people, not saying the other people here are older, and that I'm very old, but Eleni is the closest to your age. Eleni.
Thank you, Simon. So, do you think that we can unlock the secrets of an entire mountain range using just a rock that is the size of your fist? Or do you think that we can take a grain that's the size of a grain of sand and tell how old a mountain is? Well, this is something that I didn't really think was possible until I became a geologist. And what I'm going to do today is I'm going to show you that these things are possible by putting our mountains under the microscope. So I first became interested in mountains when looking at pictures like this. So mountains are quite extreme and exciting environments where that you can have a great adventure. So I was particularly interested in the ascents of some of the highest peaks, such as Edmund Hillary and Tenzing Norgay on Mount Everest, and also the adrenaline of high mountain skiing. This is something that I did a bit of myself, but maybe to a slightly smaller degree. But I found another way into the mountains, and that was through geology. I'm showing you this picture here. Now, you might recognise it because it's from the very recent series on BBC, Planet Earth with David Attenborough. Now, the reason I'm showing you this guy here, which is a snow leopard, is because that he's particularly hard to capture on camera. He's particularly elusive. And the reason being that they live in the very, very highest parts of the Himalaya. Now, this is some of the first footage that we actually captured of these magnificent creatures, and the only reason we were able to do this is by using innovative techniques and new technologies. Now, being a geologist, it's kind of similar. Mountains don't give up their secrets all that easily, and we do need to use new technologies and innovation in order to study them. Mountains, even if you don't live in them, you are benefiting from them actually. So we have the timber industries, you have rare earth elements in all of your phones, which are mined from mountains. You have great potential for hydroelectric power, and you might particularly enjoy going on holiday to the mountains. But there's a flip side to this. So mountains are dynamic and dangerous. So we not only have the risk of volcanic eruptions and avalanches and landslides, but there's also the threat of earthquakes. Now, these can have some pretty devastating impacts, such as the one in Nepal last year in 2015. This particular earthquake was devastating for the community, and it leads us to wonder what was going on beneath our feet that caused this earthquake. And this is why it's so important to understand the mountains that we have on our planet. Now, I'm going to take you to the Himalayas, which is where I do my study. So the Himalayas is 2,400 kilometres in length, and it lies to the north of India and the south of Asia. Now, how did this mountain chain form? Because it's not been on the surface of our planet forever. In fact, it's only 50 million years old. So how did it form? By the collision of two rocky continents. So our Earth's crust is the rocky part that we live on, and it's broken up into plates. These plates can move across the surface of our planet and slam into each other and collide. And this is exactly what happened when 50 million years ago, India collided and rammed straight into the southern part of Asia. And this is what formed the mountains that we see today. Now, Everest and the other surrounding mountains in the Himalaya, they are only the tip of the iceberg. So, in actual fact, our rocky crust beneath the mountain belts is very thick, a lot thicker than it is anywhere else on the planet. So as you can see, either side of the mountains, you've got the oceans where the crust, which is shaded in light, is very thin. And under the mountain belts, it's far thicker, 50 kilometres. Now this part of the mountain belt, this really deep part, is what I'm interested in. But I can't go down there, I can't go down 50 kilometres and collect these rocks, and I can't drill there either. So how am I going to be able to study them? Well, being a geologist is a little bit like being a detective. You've got to follow the clues in order to unravel a story. And to do this, first of all, you need to visit where you're going to study, which is where I do my fieldwork and collect all my rock samples. Second of all, I'm going to take them back right here to the OU where I'm going to do my analysis and unravel this story. This allows us to then build these models and understand how two continents colliding can form mountains. Gives us a lot better idea of what we see there today. So my fieldwork took me to the eastern part of the Himalayas to a little country called Bhutan, which is, as you can see, very beautiful and very mountainous. Perfect. I collected some rocks from there. Now this is a cliff that I visited, and I've just coloured in the different rocks in different shades of green to show you that even on one cliff you can see a fascinating number of rocks, and it's these rocks that you need to collect to unravel the story. So once I'd collected these rocks, I waited for them to be shipped back to the UK and then loaded them back into the back of my very small Vauxhall Corsa. So once the 100 kilograms of rocks had made it to the Open University, what I was left with was this one fist-sized lump. So it's a lot smaller than that cliff that I was at. But in actual fact, this one fist-sized piece of rock is going to tell me a lot about my mountains. Once I've got this fist-sized lump, I can take it to the lab and I can do various different things which will unlock its secrets. So this is just a couple of images that show the kind of range of things that I'll be doing day to day at the Open University. So what am I trying to investigate? Well, first of all, I want to know what's happened to these rocks during the collision of the two continents, and also I want to know when it's happened. Now, what happens when you take a rock in purple, which is sat at the top, just near the surface, when these two continents are colliding? Well, what happens is that it gets buried right down to the bottom of the mountain belt. So it starts off at quite a low pressure. You increase that pressure and you increase the stress on the rock. So it's going to undergo a change, which is what is shown as here. But also, you've brought your rock down closer to the hot core of the Earth, which means that you actually see a change in temperature and your rock gets a little bit hotter. Now, you're going to bring these rocks, which are at the bottom of the mountain belt, are no use to me. As I said, you can't get down there. It's 50 kilometres deep. I can't go down there. So you're going to need to have some kind of process which is going to bring them right back up to the surface again. So what do I do once I've got my rock? Well, I can cut it down into really thin slices and stick it under a microscope. Now, this picture here shows different minerals within my rock. Different minerals have different colours, shapes, sizes, different textures. They can be happy or unhappy, so they can be breaking down by chemical reaction, or they could be stable. And it's these minerals that I'm going to use to work out the sequence of events. So if my rock is like having a book of what's happened to the mountains, then the minerals within that rock are kind of like the chapters. So what I can do is I can take my minerals and I can look at them, and each one will tell me something about where the rock was sitting. So for instance, this mineral here tells me that the rock was very deep. Then I find another mineral that tells me that it's become shallower, and again. And you start to piece together a story which shows that this rock in particular started off at great depths and then rocketed back to the surface. So I said that these are kind of like chapters, these minerals, but say we want to have a look in greater detail and you want to kind of pick apart each paragraph, say. Well, we can do this by using new sort of innovative techniques and technologies, and one of the ways we can do this is by electron microprobe, and this is just some footage of me doing just that. So we can look at the kind of chemistry of these minerals and how they've grown in order to pick apart the finer details of this story. So we've got our story, but we don't know when it happened. So how do I work out when all of this happened? Well, as I said, you can take grains that are smaller than the sand that you find on the beach. And to do this, first of all, I have to crush down my rock, which is the first 3 images here. Now, once I've crushed down my rock, it's only some grains that are going to give me those ages, those dates of when these things happened. So I'm going to separate them out, and I end up from 1 fist-sized lump with the tiny little grains that you can see in the bottom of the jar there. And it's from those that we can get an age. So this told me that my rocks were 15 million years old. So now I have the story. So to kind of summarise all of this, I can show you that these tiny little grains can give us an age of an event that formed the mountains that you see here. And this can allow geologists to build these kind of models which help us simplify and understand the processes that drive rocks back to the surface from the deepest parts of our crust. Thank you for listening. Thank you. And next up we have Uwe.
Okay, these talks are called STEM Matters, so we will continue with the theme of matter, just a very organized form of matter, namely crystals. So I guess all of you have seen a crystal. Who has seen a crystal before? All of you. And then I will also talk about kind of a cousin of crystals, which are called quasi-crystals. So who of you knows something about quasi-crystals? Nobody. Oh, that's perfect. So you will all learn at least something, even if it's only just what a quasi-crystal is. Here's a very nice picture of crystals, if you haven't seen any before. This is a particularly nice place in Mexico. You can see a little guy there standing there, down here somewhere. So these are very, very big crystals. But what makes a crystal a crystal? Well, a crystal often has a nice shape. This is a particular crystal here, which a lot of you will know because it is actually nothing but salt. So you all have eaten crystals as well, actually. So what makes a crystal is not necessarily what it looks like, because these are little grains. Well, if you look at them under a microscope, they look like this as well. But what makes a crystal is how the atoms are arranged inside the crystal. And the atoms inside a crystal are arranged in a very particular ordered fashion. So I'm very much interested in order and disorder type things. And the order here is very simple in the sense that a salt crystal, for instance, is made of 2 types of atoms, sodium and chlorine, and they are arranged in this kind of alternating fashion, or if you want to make it a little bit more abstract, you can think of these atoms living on some kind of grid structure. So you see the green atoms and the gray atoms, and these little octahedra here mark kind of the positions of the same type of atoms that are closest to each other. That's still quite difficult for a mathematician, and 3 dimensions. Well, we can work with actually we can work with many dimensions, but it's getting easier if we limit ourselves to 2 dimensions. So a mathematician's crystal may look a bit like this. It also incidentally looks a bit like any map of Milton Keynes, where each point is a roundabout. So you can make theories that work for all kinds of different things. So what's particular about this structure? Well, it's what we call a lattice, which means that you here, in this case, is 2 dimensions. You have 2 directions, and you get all the lattice points by just starting from 1 and going a number of steps in one direction and a number of steps in the other direction. And also mathematicians' crystals never finish. They have no surface. That makes life much easier. So they go on forever in all kinds of directions. Okay, so now we have crystals. Well, people already in the 19th century wanted to have some idea of if you find a crystal, is it different from another crystal, or is it the same type of crystal? So there's always something that people want to try to categorize things into different types. Mathematicians like that actually very much, and crystallographers apparently too. So in the 19th century, they figured out that you can classify crystals by their symmetry. So what is symmetry? It's about if you have something, and in this case, it's mainly about rotation. So if you rotate it around, it may look the same again after you rotate for a while. So here's an example with a cube. If you have a cube and you rotate it around this red axis by 90 degrees, the cube will look the same. And if you have a crystal which is made up of little cubes, then rotating it around 90 degrees around such an axis will look at the same. So you have what we call a 4-fold symmetry because that's a quarter of the total angle. So you have to rotate 4 times to go back to the original direction. And for cubic symmetry, you also have 2-fold directions, which are through the midpoints of the edges. And there's even a 3-fold direction, which goes from a vertex along the long diagonal in a cube to the other vertex. If you look along that, look along this line, this purple line, then these 3 edges, these 3 corners, will form an equilateral triangle. And if you rotate by 120 degrees, the points will move onto each other and the cube will look the same. And that characterizes cubic symmetry, for instance. And there are other types of symmetries. So that was all finished by, before the end of the 19th century, we had a list of 230-something different classes, and whenever you find a crystal, you can look at the symmetry and you fit it into one of these boxes. And the reason that's possible is that there is quite a strong restriction of what symmetries can occur. And there is a result here which is called the crystallographic restriction, which again already been known in that time, of course. And it says that if I have a lattice, like my square lattice point thing I had before, in 2 or 3 dimensions, then the only symmetry that this can have can be of order 2, 3, 4, or 6. Here's a nice example of a crystal with 6-fold symmetry. This one has nice 4-fold symmetry. But you cannot have, for instance, 5, 7, 11, or something else. And this is a mathematical result, so it's true. And it won't change in 10,000 years. Whatever somebody finds, that is still true. So that allows you to find a list of all possible crystal structures. And in particular, as I said, there's no 5-fold symmetry in crystals. Well, that was everybody was happy with that until this guy came along and in 1982 discovered something that can't exist because he found a crystal which has 5 or 10-fold symmetry. And it took quite a while to get the results kind of acknowledged, at least properly acknowledged. So he eventually got the Nobel Prize for Chemistry in 2011, when actually his discovery was in 1982. So it's about 30 years afterwards. And the first reaction of people were, listen, there are textbooks about crystallography. You can read, there is a mathematical proof that what you're looking at cannot exist. This is a copy of his notebook. You can see the date here. It's April 8, 82. And he's making, what he's actually looking at is very tiny crystals under an electron microscope, much as what Eleni has shown in the first talk, just in a different way that allows you to look at the symmetry of things. And he found something there where he says 10-fold, and then there are 3, well, you can debate whether it's exclamation or question marks, probably question marks, I would say. 3 question marks. So he found something that looks like 10-fold symmetric, which he, of course, knew can't exist. That's why the question marks. Nevertheless, he pursued this and published a paper, and this is the evidence from the paper. And what you can see here is these pictures taken in the electron microscope. Actually, these are what called diffraction pictures, which can tell you the symmetry of the crystals. I don't have time to explain how these work, but what you can see there is, for instance, here you get a nice 10-fold picture, and here's another one, and then you get 6-fold pictures and 2-fold pictures here. And if you look at the angles, so this is looking at the crystal in a different direction, you'll find that it actually fits exactly with the angles you would expect in a structure that has what we call icosahedral symmetry, which is the symmetry of this body here, this icosahedron, which some of you may know if you play some interesting board games. You can get dice with 20 sides and dice with 12 sides. So this is the usual dice with 20 sides. It has 5-fold symmetry, so it can't exist in a crystal. And you can actually make these quite nice. This is a nice crystal, and it shows quasi-crystal. It's probably happy, if I used the word from before. It shows the same shape. Well, it shows a shape that also reflects the symmetry of the crystal outside, very much like a salt crystal would look like a little cube. And this is very recent, so this was just published the 8th of December. People actually found some of these quasi-crystals apparently made in outer space, in some meteorite that was found somewhere in Russia, I think in Kamchatka. Anyway, so how can that happen? I said that it's a mathematical statement. You cannot have crystals with 5-fold symmetry, full stop, or 10-fold. The thing is that in each mathematical statement, well, you start with assumptions. And our assumption was that the crystal is built on this lattice-type structure. So you have one motif, and it just repeats, like in a brick wall. There's nothing that changes. Well, we can do away with that assumption, and then we can have all kinds of symmetries. So the forbidden symmetry can only be explained if we do away with the periodicity. The structure then cannot be longer be described by my simple lattice. I have to do something more complicated. And one way of doing this is working with what we call aperiodic tilings or non-periodic tilings. And this is the best known example. It's due to Roger Penrose. Actually, he published this about 10 years before quasicrystals were discovered. And it's, as you can maybe see from this picture, it's a bit like a puzzle here. It's made out of two shapes, a darker and a lighter one. And they have kind of, like a puzzle, you can put them together in a certain way. And these particular shapes have the strange property that you can go on forever if you don't make mistakes. You can go on forever and make an arbitrary big structure, but you can never make something that repeats in the periodic way like my lattice repeats. So there's no shift translation that if I have two copies of it and I move them, they will never match again. This is Roger Penrose on a copy of his tiling, so you can see you can use it for making nice floors as well. And here's a bigger picture. And just to give you one highlight of what type of properties this has, it maybe sounds a bit complicated, but there are two notions. One is repetitivity. This is repetitive in our view, but there's also a notion which is periodicity, and this is not periodic. And I'll just try to explain that. What does repetitive mean? It means that anything I see, look for instance at this, this arrangement of 5 white tiles with a ring of blue around. Anything you see like this, you will find again. There's one here, there's one here, there's one here. You never have to go very far. There are lots of them. So that's repetitive. It is repetitive. It does keep repeating. It doesn't change. It's not completely different everywhere. But it's not periodic means that if I take this and I go on for arbitrarily far and I make an exact copy and I move the copy around, then it will never match this everywhere at once, apart from the point where I started and took the copy. So it's a much stronger property. But it is still repetitive. It looks roughly the same everywhere. And it is one model for these quasicrystals. So how can you make such tilings? Well, you can do the puzzle thing, but it is a bit difficult because actually these stones have the property that if you start doing it, you can make mistakes in the sense that it looks fine, but then suddenly nothing fits anymore. So you have to go back and forth, and it's quite complicated. So I use a simpler example to explain how to make these, which is a tiling with one shape called the pinwheel tiling. You just have one triangle. And I use a two-step process by which I first enlarge this triangle such that it has 5 times the area. And then I cut it up into 5 smaller triangles which have the same shape and size as the original one. Okay? So I marked one yellow here because it really looks exactly the same as that. And then I have some that are moved around and reflected. Well, if I can do that, I can do that again. I take these 5 triangles, I blow them up, so they are 5 times as big, and each of these 5 triangles now I cut into 5 triangles. Then I have 25. And I can do that again. I have 25, I blow them up, I cut each into 5, I have 125, and then I have 625, and then I keep going. And I get bigger and bigger arrays of triangles, and they will create a tiling that never repeats in this way, that isn't periodic in this way. And this particular one has been used in buildings in Melbourne in Australia. There's a blow up of the facade, and you can actually see that it follows this rule. So for instance, you can see that here you have a couple of these big gray triangles, which are made of 5 small gray triangles, which are exactly dissected in the way that is given by this prescription. And so you can go on forever and you create these tilings. That is one way of making them. There are also others, but there is unfortunately not time to explain. And so, well, apart from having nice quasicrystals, if you fancy to ignore your builder, if you ever build a house yourself, one task you could give them is to lay a nice floor with one of these tilings. This is a particular nice one because it has right angles, which helps a little bit, because if you use the Penrose tiling, you may want to live in a pentagon building, which probably not many of you will. And this is actually a floor in one of my colleagues' former houses, unfortunately, because he moved, and so now he doesn't have his quasi-crystal floor anymore. So, thank you very much. And I now hand on for more space, I think, to Karen.
Hi. So my name's Karen. I'm a microbiologist here at the Open University, but I don't just study normal microbes, I study extremophiles. So these are the microbes that live at the limits of life, and I'm interested in these because I can use these to understand the limits of life elsewhere in the solar system. So one of the biggest questions of our lifetime is there life elsewhere in the solar system? So we, as scientists, have to act as detectives to look for evidence. So here we have a detective on the surface of Mars looking for evidence. So what can we use as evidence? Well, for that, what we do is we look at what we can use on Earth. An example are fossils. Some of you may know that you can look for remains of life by looking for fossils. So in this picture here, we have fish. However, somehow I doubt it that we'll find fish on Mars. Another way is to look for biomolecules. In the news over the last 10 years, you would have heard some reports about methane being found and how this could potentially be a biomarker for life. Methane is a biomarker because it could be used for biological samples, for biological processes. For example, microbes produce methane. And you've all heard about cows farting. They produce a lot of methane. Somehow doubt we would find methane cows on Mars. However, we could find the microbes that produce this methane. But I find Mars is quite a boring planet. Look at it. It's dry. It just looks like a desert. To me, what is more interesting is the icy moons. So the icy moons of Jupiter. This is where we should go if we want to look for life elsewhere in the solar system. These are icy planets, icy moons, which have deep subsurface oceans. The mission, the JUICE mission, will be the first European mission to Jupiter. It will take over 7.5 years to get there, and we'll look at 3 icy planets while we're there, including Europa. Europa is one of these icy moons that we think potentially there could be evidence of life. This mission will involve 3.5 years. It will involve an array of instruments that will be looking at characterising the chemistry within the subsurface oceans, with the aim to look as if evidence of life could actually exist there. So what we want to know is, will we find evidence of life within these subsurface oceans? To do this, we need to look at the facts. What do we know about life, and what do we know about these icy moons? Let's start with the truth. We're never going to find little green man elsewhere in the solar system. I'm sorry, we're not. When we look for life, we look at Earth as an example. We're probably not going to find anything that looks like a human, or Honey G, for example. What we will find, though, potentially, I'm not saying there is life out there, is what we're looking for in microorganisms. Now, on Earth, microorganisms are everywhere. They're in your fridge freezer, they're in your cooker, they can grow in hydrothermic vents, they're everywhere. And this is how we think life evolved on Earth. We think the first forms of life were microbes. So when I, as a microbiologist, think about life elsewhere in the solar system, I imagine it's going to look something like this. So what do we know? We know that life has 3 requirements, and you probably know this yourselves. Liquid water, because liquid water is really important for cellular processes. It helps carry stuff across the cell membrane. We also have bioessential elements. We all know carbon is the building block for life, and we add nitrogen, oxygen, and hydrogen to this, and we can form fatty acids, proteins, and nuclear bases, which are the building blocks of life. We have phosphorus, which is important for ATP, which is kind of like the currency for cells, and we have sulfur, which is really important for some cellular enzyme processes. So these are what we need for life to exist. We also need an energy source. So when people say to you, you can have a chocolate bar to give you energy, it contains lots of sugars, and humans use sugars to produce energy. And that's what the 3 requirements of life for. We need liquid water, bioessential elements, and something to give us energy. So, what do we know about... Oh, if I can get it to work. Oh, anyway. What do we know about the 3 icy moons? Well, the first thing we know is that it has an icy cover, and we also know that they have a deep subsurface ocean. So when we look at places elsewhere in the solar system, we try and compare them to what we know about Earth. So we can compare the oceans of these moons with what we know about Earth. Well, let's, for example, compare Europa. Well, Europa has about a 3 billion kilometre squared volume of water compared to Earth. That's twice the amount of volume of oceans compared to Earth. And what we know about oceans on Earth, that for every one human, the amount of microbes that we have in the ocean is the equivalent to 1 trillion microbes per human on the Earth. So there's a lot of microbes within the oceans on the Earth. We know that there's bioessentials elements in the oceans on Earth, and with analysis that we've done of the icy moons from the plumes, we predict that there is carbon dioxide, so there's carbon within this water, there's hydrogen, we predict there's sulfates, and we also predict they're organics. So in theory, we could have the bioessential elements present within these subsurface oceans as well for life. Also, when we look at terrestrial oceans, we have 2 forms of energy which we can use to form life. We have light from the sun, so photosynthesis. For example, your seaweed and algae produce energy from the sun, similar to how we do with plants. And also we have these hydrothermic vents, which produce a mixture of chemicals which can be used by organisms as well to produce energy. These hydrothermic vents are really important as well from an evolutionary point of view, because this is where we think origins of life on Earth existed. So what happens here is cold water from the sea seeps through into the surface, into the vent, and the water bubbles up after being heated by the thermal processes, producing these black smokers. The black smokers are produced by sulfates particles within the water, and these can be used by microorganisms to produce energy. So when we recently, probably over the last couple of years, we've actually found evidence of geological active seafloors on some of these icy moons, which is great from a microbiology point of view, because not only can it be used as an energy source and showing that life potentially could survive in these conditions, but also there could be a place where life evolved. And that's what we need, somewhere where life can originate as well. So in summary from what I've just mentioned, that, okay, we've got water, we've got bioessential elements, we've got an energy source, and we have a potential origin for life. So when you look at it like that, why isn't there life on these icy moons? Okay, I might not be completely truthful with you. The conditions are slightly different. So for example, if we look at the pH, you look at seawater, it's between pH 7.5 and 8.3, but on Europa it's about pH 2.5. That is about the same acidity as a can of Coke. And we all know what Coke can do to your teeth, and to when you put a black penny into a can of Coke, the acidicity of it can destroy things. So you might think it's all over, nothing can grow, it's all over, there's no point looking here. Well, you're wrong. I've recently been involved in a project looking at this place. This is Dalal in Ethiopia. The pH of this water is 0.5. So I can give you your pH 2.5 and lower your pH to 0.5. I can also increase your salinity to 3 times that of seawater, and I can still get microbes to grow. That is quite impressive. So why wouldn't microbes survive elsewhere in the solar system? Also, you might notice is there's a bit of a temperature gradient here. At the bottom, you've got the hydrothermic vent, so you've got temperatures above 100 degrees. And right up the top, where the ice is, you've got cold temperatures to do with freezing of ice. But once again, all is not lost. As microbiologists are pretty, we've done quite a lot of studies around the world. And for example, we know that microbes can live within these hydrothermic vents on Earth. So once again, we know microbes the highest temperature that we have microbes growing at is 121 degrees, which is higher than the temperatures you get when you boil kettle. And also, in comparison to this, we know that microbes can live in ice. A recent paper has showed that microbes can grow at temperatures as minus 21 degrees. That is pretty cold. So, from my point of view as a microbiologist, I'm really excited about this JUICE mission. I think we've got water, we have bioessential elements, we have energy, and based on what we know about extremophiles, I really believe that we could potentially find life within these environments. So instead of you thinking there about asking me questions, I have a question for you. Are we alone in the solar system? Thank you. And our next talk is from Trevor.
Okay, right. So I'm the last speaker, and I'm afraid I've got a tough act to follow. But in the next little while, I'm going to speak about education and learning. Okay, so as was mentioned earlier, I work at the Open University here. My background was computer engineering. I studied engineering as a degree. Then I studied psychology and then education. All right, so I'm interested in how technology can be used in teaching and learning. All right, so that's my area, and that's what I'm going to talk to you about now. Okay, I have a particular approach to do that as well. So the work that I do is around a thing called participatory design. All right, so if I'm going to make technology to help you learn, who's going to be the most important person to ask? Who would you imagine? Yourselves, yeah? Learners, people, students themselves, yeah? If I want to make technology that fits your needs, I've got to work with you. And that's why we take this approach to our research, okay? So we will look at who's going to be affected by it. So I work with teachers, pupils, if it's a school context, or maybe university lecturers, if it's a university context, yeah? But it's always trying to understand me. In this case, you can probably recognize me here in the picture. That's me. And this would be people like yourselves, anyone that's involved in creating some artifact. Yeah? And it's trying to work as a team, trying to understand the expertise that each person brings to the objective, yeah, to what we're putting together. Right, so that's participatory design. Fairly straightforward in its approach. It's been around a very long time. Lots of people use it for designing products for your home and things like that. But in terms of education, it's a really key method, yeah? Because who knows best how you learn? It has to be the learner. Yeah? So that's why it's so important. Okay, I'll explain a little bit about how we do that at the Open University. My context here is distance learning. So now some of you may have came across the OU in different contexts. It's a distance learning university, so our students don't come here onto campus very often. Right? We have, our students are spread throughout the UK, yeah, and also actually some in Europe as well. It's actually fairly big. So there's about 173,000 students studying with the Open University at the moment. That's quite a lot. That's why we don't bring them onto campus. Yeah, a lot of them are studying part-time as well as doing a job or other activities that they might be involved in. So it's a very flexible way of learning, right? And they're distributed all over the country. The materials that are produced are created here, mainly at the Open University head campus, by some of the people in the room, some of the guys that have been speaking already, and some of the folks towards the back as well there. They're done by multidisciplinary teams, so there'll be the subject experts, but also educational technology people like myself, also other people like publishers and designers. Yeah, all the stuff has to look great, has to work really well for those people. Okay, so that's the distance education materials that are produced here. But as I said, our students are spread throughout the UK. Yeah, so we also have a network of about 5,000 tutors. Okay, so people that work for the university on a part-time basis to support our students. Yeah, so there's lots of students doing many different courses, but there's this huge network and organization that supports them. All right, so that's the context that we're working in. Some of the problems with distance education is that students can feel a little isolated. Yeah, there might be a couple of hundred people on their module. The degree is broken up into different subjects, into different modules. We refer to them as modules. Yeah. But they may be working on their own, but there might be a couple of hundred people on the same module, but they may not be in the same town. Yeah, so we have lots of ways to try and support each other through online materials, online forums, yeah, lots of social media stuff as and where we can. Yeah. But nonetheless, it's a sort of distributed thing. And because the materials are produced here by a group of people that aren't the same people that are actually tutoring our students, sometimes there's a little disconnect. The students don't always understand the people that have produced the materials. So the bit of technology that I'm going to explain today is the use of interactive webcasts. So as you guys know, this stuff is going out on the live on the web at the moment. It's been webcast live, but I've created a system called interactive webcasting where we use this is what the students at home would see. Here's an example of a guy doing a lab demonstration, which is a live video stream, but the students can also chat in the sort of interactive chat window, and they also have these little interactive widgets on the side. Okay. Now the reason why we do this is to enable people to see this guy's face, because he wrote the course materials, so you got a sense of who the person is. He explains the science and how it works, so it's a bit more personal than just the textbook that we send out to our students. But also the students down on the right-hand side there, they have these interactive widgets where we can ask them questions, ask them where they're from, ask them what they think the experiment's going to show, things like that. So they're making predictions prior to seeing the demonstration. And that's a very important part around this technology. Okay, so that's the context. I'll explain how it's used. So we've used it for laboratory experiments, lab casting as we call it. So this is one of the guys that's involved, Nick. He'll be setting up his experiment here. The back of the room there, you can see there's a cameraman, Chris in this case, who's doing the camera work, and the students see the image that I showed you earlier. And the reason that it's interactive is that we have these things like the map here, so the students can indicate which module they're on, and also whereabouts in the UK they are. So it gives a sense of place, a sense of a cohort, a sense of a group together. Okay, so it's an additional bit of technology. And we've been producing that with these people, so the AV people, the audio-video people, the lecturers, the students, in order to create this setup. And we can do things like this. We can ask the students what are their experiences, and every student sees this and clicks on the one that applies to them, and as they click on it, it gets the result. Right? So the idea here is that the webcast is being streamed out live, yeah? In the video, they can ask questions, students can interact with the widgets and see all the results from all the other students. So it closes a loop, closes a little conversational loop. Okay, so that's lab casting. Makes sense? See why we're doing that? All right, I've got a few nods there. It's not quite interactive, but we're getting there. The other example of this is field casting. Okay, so we talked about laboratory work for our science courses. The other work that's we've done, as you've seen earlier, we do lots of field work as well. And field work is quite important as a skill set, particularly in things like environmental science and geology, as you saw earlier. Okay, so here's the folks, here's the team again. They're out with a cameraman and they're trying to work through what they're going to show in this site. This is an example of a field site that we use actually here on campus that we did last year. With 3 presenters and the camera guys. They set up, and basically in this case, these 3 lecturers on the left-hand side are explaining here to the students the environment that they're working in. This is an environmental science course. They're asking, what is it that we could look at in this field? Let's design an experiment. And this webcast was done over 3 evenings. We did a Monday night, Wednesday night, and a Friday night for about 20 minutes at a time. Yeah, so a sort of tea time event. And we asked the students what we measure. They put their answers into a little Wordle, little widget, and it came up with the results. So they immediately saw what people were suggesting. Should we look at acidity? Should we look at soil moisture? Things like that. But it's the students that's making that decision. Yeah, the most common vote. And they also asked things like, are we going to make looking for a relationship between these things? Or are we looking for a difference between them? And again, students vote on it and say, let's come up with a research design, with an experiment design that looks for a relationship. Okay, the lecturers then came up with some example hypotheses, and the students voted as to which one shall we design the experiment to answer, which is all very good. And how are we going to sample the space? What's this area that we're going to work in, and how are we going to cover or collect our data? Yeah, so again, it's the students making that choice, making that decision. Okay, the last of this, after they had collected the data out in the field, we came back into the lab, and in this case, they were cutting samples of grass and seeing how the moisture was changing at different points in the field, at different parts of the environment. So they measured those up and got the students to analyze them. So again, here we've got what's the most appropriate graph and statistical test for this type of data. And again, the students vote in order to take it through. So in this case, the lecturers are taking them through this process of designing a field investigation, where the students are leading it and the lecturers are, if you like, doing the legwork for them out in the field. Okay? But it's a way in which we make the students' course materials come to life a little bit and still involve them in this design process and work with the lecturers here at the university. So that's what that technology has enabled us to do. I'll explain why we did that. There's some relevant theories in terms of education. So we have these things called transactional distance. So if you're doing anything mediated by technology, there's a sense that that transaction has got some sense of distance to it. And it's not necessarily just the distance in space and time, but the psychological and communication distance. So how easy is it to communicate? How much of a sense of belonging have I to these people? And these things are very important, especially in distance learning, as been shown fairly strongly. And the other thing that I mentioned was this idea of conversation being a learning through conversation. So, and again, that's driven through this bit of technology. And the last one of those example theories, is around affective theories of learning. So trying to understand people's motivations and reasons to engage in learning. And again, that's something that we've been trying to follow through this set of design. Okay, so with these technologies, what we're doing is looking at theories from education, applying them in a context, and using the technology to test and see whether or not the technology informed by that theory improves learning or not. Yeah, and we do that through this approach. Okay, so just to summarize then, we had these interactive webcasts what we're trying to do is personalize the learning experience. We've used it for some practical lab work and field work. For us, really important key for our students is making it live and interactive, because that's one of the things that there's less opportunities to do when we're doing things through email or through online virtual learning environments and things like that. Yeah. And some of this stuff, although we're doing it live, there's also options to watch the replays afterwards and also follow up with online discussions and things like that. Okay. Right, I think that's me nearly there. Just to summarize, the design-based research, which is my approach to educational research, we're looking to apply theories to learning. It's based on collaboration with folks like yourselves. And how we do that is we take the research, try to inform our practice. We do it through real context, working with schools or working with, in this case, the university courses here at the OU. But we go through this cycle of trying to analyze something to understand what happens, come up with a design, develop that design, put it into use, see how it works. And this cycle just continues, trying to refine the learning as best we can. Quite hard to do. Okay, thank you very much. I've had my 10 minutes. Wonderful.
Right, okay, so I'm going to invite our 4 speakers back up to the stage so you can ask them some questions. So we can go on to that last slide, just and there, move there. So, Gareth, if you can use one of the mics, that'd be great. Okay, so I know some of you've got to go by about 2 o'clock, so we'll ask questions for about 10 minutes. If anybody wants to stick around afterwards, then our speakers will be around for about 15, 20 minutes after we've finished here. So if you want to ask questions afterwards, that's fine as well. So can you just wait for the mic to come around? Otherwise, people who are listening on the web can't hear your question. So who's got a question for our speakers?
Hiya. This is a question for Trevor, but generally just for anyone as well, so if you want to answer, then you can. How important do you think communication and interaction is for students learning and getting qualifications, but also during your research as well?
Yeah, so the communication and interaction is, the reason that it's important is it allows you a chance to externalize, so to say what your understanding is. So if I ask you, the reason why teachers are always asking these questions is trying to understand what you do understand and maybe what you don't understand in order to try and refine it a little bit and improve. So for us, the conversational stuff and the interaction is really important, and enabling everyone to interact in a way that gives them the opportunity to say maybe what they don't understand as well as what they do understand. So for the learning context, it's a key one. Yeah. Thank you.
Okay, I'll ask a question of Eleni while we're waiting. So I'm kind of curious. I've always been curious about this. I've known geologists for a long time, and you talk about these thin sections. How thin is a thin section, and how do you make it?
So my thin sections are 30 microns thick. What
does that mean in...
a micrometer is, so you have 10 to the minus 6 meters, if that makes any sense. So very, very thin. So it's kind of, it's thicker than a hair. And the way that you make it is by, you take it to the rock cutting lab. So you start off with your lump of rock, and then you'll cut it in half, and you'll choose the part that you're particularly interested in. You'll then end up with a kind of a rock chip, which is quite thick, of that particular bit you're interested in. You'll then mount it on a piece of glass, and then you grind away at that top surface, and you get a really nice polish on it, and then that's what you use.
Cool.
Yeah.
Thank you. There you go, I learned something. Okay, do you want to ask a question?
Okay, I have a question for Karen. The icy moon composition, how did you determine that? What tests did you do?
I didn't do any of it. It's a whole team. So there's a lot of telescope work that's going on at the moment, looking spectrometers, looking at the composition of the plumes, trying to estimate from that. So it's a bit of an estimate at the moment what's going on. So hopefully with the JUICE mission we'll have a better idea of the compositions. And that's what the idea of is, particularly with Europa, is seeing if they can look at the compositions to see if all the what we know that we need for life is present. So we know there's water there, are the bioessential elements there, is there an energy source? So that's kind of what they're doing at the moment. So it's a lot of, it's not my field of expertise, the actual analysis, it's more the physicists, and I'm sure, you know, you guys, when you finish university and are working for NASA or for the European Space Agency, will be able to come here and tell us more about it. So it's a lot more more analysis that's going on at the moment.
Okay, next question.
Hi there. I have a question for Eleni. When you were talking about dating the mineral that was as small as a sand grain,
Yeah.
and you showed, I think, a microscope picture of that, and it had lots of little holes in.
Yes.
So could you say a little bit more about how you do that and what you do that with?
Yeah, sure. So what was happening there? So you've got your grain that you're going to date and find out an age. And the reason that you can find a date from that particular mineral is that because it's got high concentrations of radiogenic elements, so things like uranium that break down to lead through radioactive decay. So when your mineral first forms, it's going to have lots of uranium in, but maybe not very much lead, which is the daughter product. And then over time, millions of years, you'll end up with more and more lead because your uranium is breaking down to that lead. Now, it's the ratio of those two things that we want to measure. And the way that we do that is by taking the grain, and you then have a laser, and you ablate part of that grain. So what you're doing is you're firing a laser at that grain, a really pinpointed laser, and then that's going to release some of the atoms, which you can then collect and measure using something called a mass spectrometer. So what all that's doing really is giving you this ratio, and from that ratio, because uranium has a specific decay constant, so it's always going to be producing the same amount of lead throughout time, that ratio gives you a really accurate age on that particular mineral. So that's how you date the rock, is by taking those grains. Yeah.
Okay, next question.
This is a question for Eleni again. So you say in a cliff that you have different types of rocks. Mm-hmm. How would you know which rock to choose? And then further from that, you say that you split the rock in half to choose a mineral. What mineral would be best for you to determine the date?
Sure. So when you're faced with a cliff, with an outcrop, so one of the first things you learn when you start a geology degree is kind of, a lot of geology is very observational. So you're looking for differences between different rocks. So my cliffs have been really through the mill, and the Himalayas has messed everything up. But originally they would have been sediments on seafloors, maybe some lavas, basalts. So that's what gives you the different kind of rock types that are sat alongside each other. For my study, I'm interested in all of them, because if you take lots of different rock types, you get different parts of the story. So you might want to focus your study into one particular type. So maybe you're interested in granite or sandstone. But in order to understand a big region, like a mountain belt, you want to kind of look at everything. When I cut the rock in half, which bits I'm interested in, well, again, you're kind of interested in everything to start with, and then you start to narrow in what's the most interesting part. So I'm really interested in garnets, which you guys might know, really sort of red minerals. So they're quite obvious to see. Other minerals, such as the tiny little grains, which contain lots of uranium, they're called zircon. They're really hard to see by eye, so you won't know until you've cut it open and you get it under the microscope. Hope that answers your question.
Cool. Any more questions?
You talked about extremophiles in outer planets, but how much do we know about those that are actually on planet Earth?
So we don't know we don't really know much about the outer, the ones outside the Earth. It's all been done with simulation. We know we've got increasing knowledge about extremophiles on Earth. So we have microbes that can live in acid and alkaline conditions, high temperature, cold temperatures. I've done some work on the International Space Station where we sent microbes, extremophiles, up onto the International Space Station for 2.5 years. Tim Peake brought them back down, and we know microbes can grow once they've been exposed to space. So we're growing a lot of knowledge on extremophiles. It's a really interesting point, research, not just from what I do, because I also have a biotechnology viewpoint as well. The enzymes you can use, for example, in your washing powder come from extremophiles. and from in the paper mill industry, we use a lot of enzymes from extreme environments. So we do have we know quite a lot, and we know the physiology behind it, mostly what they do. So no, it's a really interesting area to get into, and we can extrapolate what we know on Earth and what we know under these conditions that we've modelled. So with data particular for Mars, we know quite a lot from the Mars Science Lab mission. We know the composition of what it would have been on early Mars, so we kind of can predict what the conditions would have been, and then we can look at like analog sites, so similar sites to what we have on Earth, and we can start looking at them as kind of like an analog for this kind of life.
Cool. Okay, I've got one last question, which I'm going to ask of Uwe, because I'm intrigued. You told a lovely story there about a discovery made, or potential discovery made in 1982, and then a Nobel Prize awarded in 2011, I think. Yes. So I'm kind of curious as to when you started to get interested in quasar crystals, and did you get interested because you thought this dude was right, or because you thought they were wrong?
I have to remember, actually, it's a long time ago. Because I started as a physicist, actually, before I became a mathematician somehow. And so I was interested in magnetic systems mainly. And when these quasicrystals came along, I was interested in how magnetic order may kind of interact with this weird spatial order. That must have been around the time when was that? 1992, roughly. So about 10 years after the discovery, I think. By that time, I think it was generally accepted that it was right. It didn't take till 2011. I think it would probably take about 3-4 years. Although there was quite a lot of controversial discussion in the literature still, because there was another actually a double Nobel Prize laureate who didn't like to believe it, Linus Pauling, who didn't like to believe in it, and he wrote a lot of articles saying that this was nonsense and it was all cubic crystals which just had very big unit cells with 20,000 atoms in it, and, or something like that. But yeah, it was generally accepted at the time, I think.
Okay, thank you very much. Okay, so I'm going to stop the questions there, but I say if you want to stick around, our 4 speakers will be around for a little bit longer. Can I just ask you before you go, you've all started to fill in your sheets, I see already, so if you could just, if you've done the before bit of your sheets, if you turn over, you've got an after bit, so if you could just complete that before you leave, and there's a little box there with Gareth, if you can just raise his hand, yeah, if you can just drop them in there before you go. Just a couple of thank yous before we finish off. Obviously, I'd like to thank our 4 wonderful speakers. I'd also like to thank a few of the people who've helped put today together. So we've got Diane Ford looking rather embarrassed over there because she never likes being pointed out. Anthony Steve from Denby, just down there. He's also not going to put his hand up. Simon Kelly, you introduced us today. Kate Bradshaw, who wonderfully comes along and does our photos for us every year. And Gareth Davis. And finally, our lovely AV team who do this wonderfully every year. So if you'd just like to give them a round of applause, so thank you. Then you just need to follow your teacher's instructions now. I say, if you want to speak to our speakers, they're just up the front. And thank you very much for coming. Have a lovely Christmas.